This is just a quick reminder that you should feel free to pause the video if you ever feel you want more time to think and write. Welcome everybody to day 2 of section 5.1, inverses of relations and functions. Big question today is, how does a relation compare to its inverse on a table, on a graph, and what do the equations look like? So let's say you've got a function like f of x is equal to 2x minus 3. One thing you can do is you can change the f of x to a y, and you can, and so it becomes y equals 2x minus 3, and then you can interchange the x and the y. That's a really great way to produce the inverse. Just flip them. Wherever you see a y, write an x, and wherever you see an x, write a y, and it becomes x equals 2y minus 3. Then you can solve for y, as you can see here, solve for y, and you get y all by itself. And then instead of writing y again, you can write this notation right here. This means the inverse of f. That means we had a function f, and now this is the inverse of it. This is not an exponent, it's a notation, function notation. It's inverse of f of x is equal to what you see here, x plus 3 over 2. So that means 2x minus 3 and x plus 3 over 2 are inverses of each other. And what does that look like on the table? Well, you can see here we just made a standard -1, 0, 2, 3 kind of a table, input-output table, and we chose the input and we calculated the output using this function. Well, then if we had the same exact table for this, it would be flipped. We've had what used to be the input is now the output. What used to be the output is now the input. What used to be a y-intercept is now an x-intercept. And if you put -5 into this function, it would be -5 plus 3 is -2 divided by 2 is -1. That's the output here, -1. These tables are inverses of each other. And then if you looked on a graph and you plotted those points, you can see here's the original 2x minus 3, and here's the inverse x plus 3 over 2. And what you'll notice is that they're reflections of each other across the line y equals x. The line y equals x is a dot. It's like a mirror right here, and what used to be on this side now gets flipped over to the other side. So let's take another example. Consider this function, that x cubed plus 2. We want to know, is it 1 to 1? Is it what is its inverse, and what do the graphs look like? So you can ask yourself, does it pass the horizontal line test? If you want to know if it's 1 to 1, you can graph it and find that yes, it's actually always increasing. It's this gray graph right here, x cubed plus 2. This gray graph, x cubed plus 2, it's like the x cubed graph, except it's been vertically shifted up 2 units. And it is always increasing, therefore it is 1 to 1. It passes the horizontal line test. If you want to know what is its inverse, you can flip the x's and the y's. This becomes y equals x cubed plus 2, and then you switch them. X equals y cubed plus 2. And the rest of it is just solving for y. So maybe move the plus 2 over to the other side to get x minus 2. Take the cube root of both sides to leave yourself with just y. And then it becomes the inverse of g. Remember that it's a g function, so the inverse of g would be equal to cube root of x minus 2. What does that look like on a table? Well, if we take these original values of -2, -1, 0, 1, and 2, you put them into the g function, you get these values, cube them, add 2, and then you get these values here, -6, 1, 2, 3, and 10. And you can plot them on the graph, and they kind of look like this on the gray graph. Now, if you were going to do find the inverse, then you can see 2 used to go to 10. 2 was the input for 10. So now 10 is the input, and 2 is the output. That's confirmed with the equation that we have. You could say 10 minus 2 is 8. Take the cube root of that, and you get 2. 3 minus 2 is 1. Take the cube root of that, and you get 1. 2 minus 2 is 0, becomes 0. And -1, the cube root of -1, you have to ask yourself what number times itself 3 times is -1? Well, it's -1. And it's confirmed, as you can see from here in the table. -1 used to be the input, and now +1 is the output. Now here, 1 is the input, and -1 is the output. So I want you to figure out what should go right here. And you can use the table or you can use the equation or both to confirm. In any case, what you get is you get this red graph, and you can see it's been flipped over the line y equals x. 210 goes down to 10, 2. 0, 2 goes down to 2, 4. Negative 6, negative 2 goes down to negative 2, negative 6. Inverses. Let's say we compose them within each other. Let's figure out what is f inverse, f composed in f of. Let me say that again. Let's see what the composition of f composed in f inverse is. Well, as you can see, you can always rewrite it as f of f inverse of x. And so now the rest of it just becomes figuring out what the actual equations are. You can take, we know what f inverse is. It's this cube root of x minus 2. We're going to plug all of that into the f function. The f function is here x cubed plus 2. So we take everything that was in here for x and we put it in. We say that that's the input. Then we cube it plus 2. Well, the cube and the cube root will cancel. We get x minus 2 plus 2. And therefore, we just get x. All of the operations cancel each other out. And that's to be expected. In fact, you do the same thing in the opposite order. You take the inverse of f of x, and replace f of x with what the function in that is. It's x cubed plus 2. Then you see we can take all of x cubed plus 2 and put it into the f inverse function here where x used to be. This used to be an x, and now it's x cubed plus 2 because that's what we're trying to evaluate. The plus 2 and the minus 2 cancel, and the cubed and the cube root cancel, and we're just left with x. You can see that for each function, if it's 1-to-1, then you should be able to compose them and cancel, get down to x each time. Doesn't matter what the 1-to-1 function is. Let's talk about restricting a domain. And before we talk about restricting a domain, I'd just like to let you know that the nitrogen, the 7th element on the periodic table, is our audio check fact for the day. That's nitrogen. Anyway, check this out. We've got a function that is not 1-to-1, and its inverse is not a function. It fails the horizontal line test because it has more than one intersection. You are able to draw a horizontal line and that intersects the graph twice. So it has more than one intersection. Therefore, if you were to flip it over the line y equals x, like this, then it would become something that would fail the vertical line test. So therefore, its inverse is not a function. It is not 1-to-1. And you can predict that looking at its inverse also. If you were to do the same process we did before, change f of x to y and then flip the x and the y, isolating y, eventually you have to take the square root of both sides, and you get plus or minus square root of x minus plus 2 is equal to y. And if you were to try and say that that's what the inverse function is, well, this plus or minus thing, that's not a function. You get exactly 2 values out for many of these values of x. So it's not a function, as is. But what if we changed it? What if we restricted the domain? What if we didn't keep both halves of the parabola, both arms, the left arm and the right arm, but what if we just kept the right arm? All of a sudden, this gray thing is a graph that passes the horizontal line test. You're allowed to do this. You can say, okay, we're just going to take, instead of just x squared, we're going to take the values of x squared that are all greater than or equal to 0. Starting here, going up, this passes the horizontal line test. So therefore, its inverse will pass the vertical line test. The inverse is a function. And that's one reason to restrict the domain, to come up with functions that, yes, do pass the horizontal line test, that are 1-to-1, and whose inverses do have functions. That's what we have for today. I'd like you to start assignment 5A2 by copying the problem list, do the first problem, and I will see you in class.